Hello, everybody. Let us start our discussion today. So, this is the second experiment that we are going to learn, and its explanation that came. Photoelectric effect has a quite bit of history. So, let us start discussing it one by one. The history starts. The history is quite interesting. You remember that the classical theory. This is essentially Maxwell's electrodynamics. So, this came in 1860s. Okay. Okay, so before I go any further, let me tell you that the way we are trying to develop our discussion today is kind of quite historically. First, we will start by discussing something which was observed new, and then people did more experiment on what is observed new. They found some interesting properties, and then people try to explain them using the classical theory of radiation, which is what came in 1860s, and it didn't work. And then in 1905, Einstein had to come up with some new theory, which is eventually will explain this. And then Einstein will not only come up with a new theory, he will also propose something that this you will see if you do good enough experiment. And eventually, that is also what was observed. So we will develop our discussion in this particular way. All right. So let us start. So this was the start. Then, so this was a theory which predicted electromagnetic wave. Somebody had to show that the electromagnetic wave existed, and that was done by Heinrich Hertz. So this is where he is first time showing that electromagnetic wave existed. How did he do this? So he had a transmitter. The transmitter was very simple. So he had what we call spark plug. So two metal electrodes kept very close to each other, given very high voltage difference between them. So it emits radiation. It emits spark. Spark, we see, spark is nothing but light, which is electromagnetic radiation. So it turns out that such a transmitter, spark plug, emits radiation in many different frequencies. And then he had a receiver kept in a little distant away. And what you expect is to see a spark in this receiver, because you remember that you have the electromagnetic wave which has the electric fields. The electric fields, the direction of the electric field in this electromagnetic wave will be like this, because say one is highly positive charge and one is highly negative charge. And then when this radiation comes into the receiver, so this is transmitter and this is receiver, then there will be electric field difference between these two electrodes, and that will create another spark. So, or if you put an ammeter over here, you will see if you put an ammeter over here, you will see a current in that ammeter. So that is how we try to observe whether, so once the spark is produced here, so you will see a deflection in the ammeter needle. This is what he saw, and that proved the existence of electromagnetic wave. You cannot use this wave in not much useful sense, which was done later by Jagadish Chandra Bose, who invented the millimeter waves, and then the radios, all the communications came about. But it was Heinrich Hertz in 1887 first showing the existence of electromagnetic wave. He saw something more interesting in this. So he observed that the receiver sees more sparks if it is kept in a lighted room. So if you have the room which has light in it, so you have just turn on the light switch of that room, somehow the receiver is receiving more spark. And you may think that it is just directly coming from the lights in the room, but that may not be quite true, because the lights in the room will not emit radiation which will have enough electric field to create this pulse. But this is still what you observed, and this was something that's puzzled Hirsch and other people, and people started developing experiments to see this effect. Okay. Now, this is essentially what will turn out to be the photoelectric effect, which will essentially let Einstein hypothesize that radiation is more like comes in discrete packages like particles. And you see, Henry Karge is trying to prove that the radiation is a wave, getting a clue from his experiment for the first time that the radiation may also be like particles. Okay, so that's the irony of physics, if you wish. But anyway, so once this is observed, the next person who did really a lot of work to understand this is Stoletov. And he did these experiments between 1888 and 1891. And we need to discuss this a little bit more detail, because this is where the first time qualitative properties are being learned. Okay. So he devised a setup, and this is the setup the basic setup what we use today is almost the same. So, and you have an experiment in your PHY-101 physics lab, which essentially uses the same setup to to reproduce the exact same result as Stoletov saw. Stoletov's experiment was not as good, because you can imagine he's first time designing the setup, and nothing is much is known about this mysterious phenomena at that time. Once you know about the phenomena, you can always design a better setup. But nevertheless, let us discuss uh, the setup that Stoletov made, and your lab also uses the similar setup. The setup is the following. So you have a half cylindrical metal plate here, and in front of that you have a metal ring means that the inside is empty, so it's a metal ring kind of thing. Okay, so if I wish, I can make light fall through this ring. It will go through the empty part of the ring and fall in this uh, the half cylinder plate. Okay, so let's give them name. You will see why I call them A and C, these very strange names, but let's call them A and C. Now, this entire thing is obviously kept in a chamber. If you wish, it's like a bulb. Okay, and at time of Stoletov, they used quartz, but nowadays you can use glass also, because you will see why. Once I explain to you what is happening here, you will see why you can now use different things. But anyway, so the idea is that the radiation can come and fall from this left hand side, and you have these, and there are metal electrodes which are coming out of this, which I can make in a circuit. So what I have, I first keep an ammeter here. So this ammeter is very sensitive, can measure nanoampere currents. I have what I call a voltage divider bias. So let me explain to you what is a voltage divider bias, and then I will come back to the circuit. This is something that we use in many places in experiment. Maybe you already know it, but there's no harm in repeating it. So what you want to do is you want to use a battery. Say I have a battery like this, A battery is a collection of cells. So this is a battery, and so there is a certain voltage, so let's call V0 across the battery. So the total voltage in the battery is V0. If it's like 1.5 volt battery, the V0 is 4.5, 1.5 into 3, because I have drawn 3 cells here. 1.5 volt cells will give you, 3 cells will give you 4.5 volt. Now, but out of this, I want here in my output terminal, I want a varying voltage. So I want a voltage which can vary. So vary, I give this sign. Okay. So what do I do? So I connect a resistance over here. Okay. So this resistance, let's call the resistance is R. One end I connect with output, I connect here. The other end connects to somewhere in between the resistance, such that you know that the resistance is made up of a wire, and the resistivity, once you know, if you multiply by the length, you will get the resistance. The resistance is proportional to the length of the resistance. So here I say I get a resistance R1 and the rest is R2, such that R1 plus R2 is R. Now if I ask what is the resistance between these two terminals, output terminals, you will see that the resistance, the voltage drop across R is V0. So the current flowing through this is I. And in between the terminals, say output 1 and output 2, the voltage will be the voltage seen by the resistance R2. So that resistance will be R2 times I. So V, varying V, will be R2 times I. R2 I can change by changing the position of this needle. And this is R2 times I is V0 by the total resistance R. So because this resistance divides the voltage into two parts, it's called a voltage divider bias. So if I want to change the voltage, I use a voltage divider bias. So here I have the resistance of the voltage divider bias. One side is directly connected. The other side is connected through a needle. Okay. But you see, this setup can still provide a voltage from 0 to certain volt. What if I want to get a little bit more creative? I want some negative voltage. So for that, what I use is what is called a commutator. So let me draw it and then explain how it works. So I have these two ends, which is what will go to the circuit, and the other, I have two ends, which are this is not connected there, and this, and these are connected to the battery. Okay. Now you see what happens. So let me give them some name, P, Q, R, S. If I connect P with S and Q with R, then what happens? You know that this end of the battery is negative and this end of the battery is positive. So if I connect P with S, then C becomes positive. Right? If I connect P with S, C becomes positive, and Q with R, A becomes negative. On the other hand, if I connect P with Q and S with R, so S with R, so now A becomes, P with Q and S with R, yes. So now A will become positive and C will become negative. Okay. So in this experiment, default, we'll see why, default is C negative. Okay. C stands for cathode. And 8 stands for anode. Cathode is something which is negative. Anode is something which is usually kept positive. As we see that we have a voltage divider bias here. Sorry, we have a commutator here. So this setup is called commutator. Earlier days when we used to do experiments in our labs, there was a very interesting Mercury and rocker arrangement for the commutator. Now it is just a switch. But anyway, so the default position of the commutator is such that C is a cathode and A is an anode. Okay, so now the question is what he did and what he saw. Okay, so we are discussing Stoletov's experiment, Stoletov's observations. See, I have two things to measure. One is the voltage, which I can change, and then I can measure what is the current across the voltage. To measure the voltage, I need a voltmeter, which I forgot to put it. So I have a voltmeter here. Okay. So what he will do is he will change the voltage, which I have. I can use the voltage divider bias to change the voltage. Let the light fall in through the hole of the anode to the cathode and measure the current. Okay. This is what he is trying to do. So, and as I said, that default, so the first observation is with negative to cathode. So if I do this, this is a very famous type of observation. This is done for any electric devices. This is the basic observation that one wants to do. It's called IV characteristics or voltage current characteristics. Here voltage is my control variable and I is the current. Okay, so what did he do? So he changed the voltage and it was observed that there is some current at V equals to 0. So first observation is current at, there is, so what I'm plotting here in the y-axis is, let me call this small I instead of a capital I, because that is what one uses for changing current. Okay, constant current I is used. I will use this V equals to 0. Okay, so this is I, small I. Small I is the changing current. And I will use capital I for intensity of the light. So what you saw is if you shine light with intensity, some non-zero intensity, you get a current at V equals to 0. That is odd because usually we know that you need to give some voltage to get current. Ohm's law, V is equals to I times R. That is not what you observed. What happens if I change the voltage? As I increase the voltage, the current increases and after certain voltage it becomes constant. It doesn't change anymore. So this happens once your light is at certain intensity. Say let's call it I1. If I change the intensity of the light, the current at V equals to 0 is different. So here you will see a different current. It will again rise and it will get a different constant value. So this is I2 and I1 is greater than I2. So I1 is, if you have more intensity, you see more current. If you have less intensity, you see less current. So Stoletov also did that. So these are called saturation current, just because as it increases the voltage, it doesn't increase anymore. So what did Stoletov do? He plotted the intensity versus saturation current. So let me call it ISAT. And it was like 0 intensity, 0 saturation current and linear, completely linear relation. Now when Stoletov is doing these experiments, we did not have the concept of electron. remember, Stoletov is doing these experiments during, this is Rudolf Hertz. Stoletov is doing 1888 to 1891. J.J. Thomson discovered the electron in 1889. So while Stoletov is doing these experiments. So J.J. Thomson, and we'll see something interesting happened with J.J. Thomson and his son later in the course. So he discovered that these cathode rays, which are made up of these small particles, which was named as electron eventually, this happened in 1889. Okay. So it was realized that, okay, so electrons has this negatively charged, and the current, that when you say positive current, it means flow of negatively charged particles. So it was realized that what is happening here is, as the light falling into the cathode, there is some electron which is coming out of the cathode, they are going towards the anode and getting collected, because you see the current. So there is no connection between the cathode and the anode, but still you see current, which means there must be some electron going from the cathode to anode. So there is, we will call that there is a current going from anode to cathode, right? So this is after the discovery of electron, this was understood that there must be these electrons are collected, then collected by the anode, and that produces the current. Light of more intensity produces more electron. So that is why the saturation current is different for different intensity. Okay. There is one more observation done by Stoletov, which I have placed here to write, is that this was called photoelectric effect, because it was understood, because its electron is coming out because of photo means light. This was called photoelectric effect. And the electrons are called photoelectrons. Okay. So the other observation of Stoletov was the emission of photoelectron was almost instantaneous. Okay, so what does it mean? It means that you remember that for I equals to 0, you see no saturation current, no current at all. Now, I have this kept in this glass chamber. Say I put a cover in the chamber. Immediately, there is no electron coming out. There is no current registered. The voltage is kept to 0. I put a cover over the tube. This, now you can call this photo tube, and no electron coming out, no current registered. Immediately I lift the cover, I start to see a current registered. Okay. Okay, remember this current is coming in order of nanoampere, so it's a very, very small current. So if I have a 100 ohm resistor and I am applying 10 volt, I expect current to be 10 volt by 100, which is 0.1 ampere, right? So this is in nanoampere. It's extremely feeble current, which you will not see if you are not really trying to measure it. So you need a very sensitive ampere meter, ammeter. Now this is quite puzzling because it was known that this type of electron emission was known earlier. Even so, this is different from thermoionic emission. So what is this? So this was known earlier that if I have a metal and I have a filament to heat up the metal, so I draw a filament like this, just like the old bulb you have, then this emits light. It emits heat and light. So that's how the old bulbs work. But for this to happen, if you have seen in your lifetime when you were very young, the older light bulbs, the incandescent light bulbs, where you put on the switch, some yellow light comes out of the bulb, and if you remember that it takes some time, it takes a little time, maybe half a second or 1/4 of a second, for the bulb to get its full glow. Okay. So there, what is happening is that you are giving it current, and light is coming out of it. There are experiments where people saw that if you heat up a metal plate, the electrons come out of it. Okay, but it takes again some time. So it's not it's different from thermoionic emission, because as Toletov observed that the emission of photoelectron was almost instantaneous. It doesn't take almost any time. Now after this, there were more detailed experiment developed by Philip Lenard's. And these were done between 1900 and 1902. So what he did, well, till now we have not talked about making the cathode positive. The cathode is initially, Toletov experiment is always kept negative and the anode positive. We also have not talked about light of what color or frequency. We just said light falling into it. Toletov has changed the intensity, but he has not talked about the color of light, right, or the frequency of light. So that these are the two things which were introduced by Philip Lenard. So Philip Lenard said that he will observe the exact same thing. So voltage versus current plot. Okay. And now you see that you understand that there are these electrons coming out of the cathode. Where is my cathode? So it's electrons coming out of the cathode. And if I say these are my electrons coming out of the cathode, and they're going towards the anode and getting captured by the anode. So there must be a velocity in the right hand direction of the electron, and this velocity in the right hand direction of the electron can be reduced if I change the bias. If I make the cathode positive and the anode negative, because the anode is negative, now the electron will get repelled by the anode and they may not be able to reach the anode, right? So Philip Lenard tried both in forward and reverse bias. So forward bias means V greater than 0, cathode is negative, anode is positive. So we call that V greater than 0. When anode is positive and cathode is negative, reverse bias is ulta. V is less than 0, C is negative, C is positive, cathode is kept positive, A is negative. And that you can do using that commutator we discussed. So what did he saw? So he drew the same curves. When it's in forward bias, it shows that trend. If you use a different intensity, it almost follow a parallel line. So this is I1, say, and this is I2. And remember, I1 is greater than I2. If I draw like this. If you apply the reverse bias, so you are now changing the voltage negative, so you are giving more and more, as the voltage is getting more and more negative, you are getting more and more resistance or repulsion to the electrons, and they will not be able to reach the anode. So the current decreases and it goes to 0 at some point. For a different intensity, higher intensity, it goes to 0 at some different point. I'm sorry. So let me let me bring in something more, because otherwise you will get confused. Okay. And let us draw for a given color now. Okay. So now Philip Leonard is also using light of a particular wavelength or frequency. So I am drawing with one color here. The same color frequency but a different intensity. Okay. So light of and now something mysterious was observed. It's not that only this is going to 0, so it's after that it will remain 0 if you decrease the voltage further. But for if I have changed the intensity, I1 has greater intensity than I2, but the frequency is same, and then you see that they goes to 0 exactly at the same frequency. So all intensities of a given frequency requires same reverse bias. Okay, so you use a filter to select a particular frequency of light to fall into your cathode, and then you apply a reverse bias and you change the intensity. The saturation current changes, but the voltage at which it goes to 0 is same if the frequency of the light is not changed. So this voltage is called stopping potential. So what do you conclude from this? You say that, remember, the electrons were coming out from the cathode and conducted by the anode, which produce the current. The electrons are not being able to reach the anode because you have produced a negative voltage across the cathode and anode. So this negative voltage must opposing the maximum kinetic energy that these photoelectrons have. So I can now say that the maximum kinetic energy the photoelectrons have is V0, because that is the amount of energy. V0 times E is the amount of energy that I have produced to stop them. Okay. So this is one observation of Philip Leonard. The other observation is, now once you see that irrespective of the intensity at this particular frequency, you see the stopping potential is same. He used different color light now. So this is one colored light, and these two colored lights say have the same intensity. Okay, same intensity, two different colored light. So these two different colored light now happen to have this different stopping potential. So same intensity, different frequency. If you use this, same intensity will give you same saturation current, but different stopping potential. Okay, and one more observation is, higher frequency so what I call V0 is this distance. So let's call this V01 and this V02, and this as nu1 and this as nu2. Higher frequency requires higher stopping potential or higher reverse negative bias. So here nu2 is greater than nu1. Okay, V02 is greater than V01. V02 is the modulus of the voltage, so V02 is more negative, so that negative number is obviously lesser than V01, but you need more reverse bias, that is the point. Okay, so these were all the observations that existed at this point. So this is, we are talking about 1902, 1903, and let us try to see that if this can be explained using our theory of light, which is the Maxwell's electrodynamics. Okay, so can we explain the photoelectric effect using electrodynamics? Or electromagnetic theory of radiation? Well, for that, let us assume something. Let us say that, see, this gives you EM wave, right? Now the wave has its energy distributed over a very large region of space. So say we are talking about a source which is emitting the light for the photoelectric effect, which has a power, emission power is P, which means that it emits P watts of light, which is P joule per unit time per second. So this is kept at a distance R from the metal in which the light is falling. Okay, so how much light, so power, and this is emitting isotropically, so power per unit area at the metal surface, how much will it be? Well, P is the power that the source is emitting, and if the metal surface is kept at a distance r, then by the time it has gone a distance r, the entire power is now distributed at 4 pi r square area, because that is like it's a point source and it's going out to the entire sphere. So this is the power per unit area at the metal surface. Now if one metal atom, see what is our idea of where will the electron come from? You have the atom, and then from the in the atom there is an electron in the atom, say outermost orbit, and that electron will try to come out, right? So if one atom have dimension A, received emission, so how much emission will it receive? It will receive an area P into, say, A square. Okay, so forget about 4 pi because we are doing rough calculation. So this is P A square by R square. So this is the amount of emission that the atom will receive, right? All right. So this is the received emission, but remember P is the power. So this is received emission per unit time. So in time t, capital T, say, total emission received So this is received by that electron in the atom. Actually, at that time, the atomic electrons theory is not known. So you are just assuming that the electron is somewhere there in the atom, but it will receive this much amount of energy, right? So this is the energy that it will receive. Now, if the electron has to come out, the electron should have this much amount of energy should be equals to the electron the energy that it shows when it comes out from the metal. So it should get all this energy when it is coming out of the metal. So when it is getting all this energy, at least this much of energy is required. So this EV, this V is, let's call V0, which is the stopping potential. So remember that stopping potential gave us the maximum kinetic energy that the electron can have, right? The stopping potential gave us the maximum kinetic energy the photoelectron will have V0, right? So these electrons which has come out of the metal should have at least this much of energy. So V0 times E is actually in the proper energy unit. Now once I have this, I can calculate T. So let's say that P is the power of the light is say 10 watt, which is typically fine. A atomic dimension is about 10 to the minus 10 meter, 1 angstrom. Say the source is kept at a distance of 1 meter, and V0 for these metals is about, say, 1 electron volt. E we already know. So if you calculate the time, it will come out of the order of 10 seconds. The homework is to calculate it exactly. It will come out to be around of the order of 10 seconds. It can be 3 seconds, it can be 30 seconds. I don't bother, because both 3 and 30 is much larger than what you will call instantaneous. So the electromagnetic theory, if I use, I will get that the energy that it is, the time that it takes for the photo emission to happen is 10 seconds. So for 10 seconds, the light has to be absorbed by that atom for the electron to come out with that at least that much of stopping potential. And it was observed that it is happening instantaneously. So definitely this doesn't work. Also, we have not studied the electromagnetic theory, Maxwellian electromagnetic dynamics, but the Maxwellian electrodynamics, the energy explicitly does not depend on the frequency of the light, which is what we observe here. The different frequency has different amount of photoelectron energy. Or photoelectrons emitted because of different frequency has different amount of photoelectron energy. So that also does not work. So we have seen this photoelectric effect, which cannot be explained, the observations cannot be explained using the electromagnetic theory of light. So we need some new explanations, and that is what came from Albert Einstein. Now I'll just read a little bit from his paper, just I did for the special relativity case. It came, interestingly, these two papers came in the same year. 5 different papers came in the year of 1905, where Einstein changed a bulk of the physics understandings. And this paper explained many things. It also had a better explanation of black body radiation. But anyway, so he says that indeed, it seems to me that observation of black body radiation, photoluminescence, which is for different phenomena, production of cathode rays by ultraviolet light, which is photoelectric effect, and other related phenomena associated with the emission or transmission of light appear more readily understood if one assumes that the energy of light is discontinuously distributed in space. According to the assumption considered here, in the propagation of light ray emitted from a point source, the energy is not distributed continuously over ever increasing volume of space, which is he is referring to the radiation, the wave theory of radiation. So in that wave theory, the energy is distributed over the entire space. So he's saying it is not like that, but consists of finite number of energy quanta localized at points of space that move without dividing and can be absorbed or generated only as complete units. So this is called light quanta hypothesis. So what is the hypothesis? The hypothesis is that energy of radiation consists of a finite number of energy quanta. This is what we call photon today. Localized in space and travels at the speed of light undividedly. So travels and exchanges also. So when energy is exchanged between, say, atomic oscillator and this, it is also done undividedly. So this energy per photon. So this is not Planck's hypothesis. This is the energy of a light quanta. Planck was saying that the energy exchange between the atomic oscillators and the radiation is in quanta. So this is the energy of the light itself is given by h times its frequency. Okay. So this was the light quanta hypothesis, and in the rest of the discussion in next 5 minutes, we'll try to understand how it explains the photoelectric effect. First of all, because the energy is not distributed in the entire space, so we realize that if an electron encounters a photon, it can get h nu energy instantaneously. Okay. So that explains the instantaneity of the effect. More intensity of a given frequency of light, this means more photons. Okay. These two are readily understood. So more intensity, more photons, so which means that the Stoletov second curve is readily understood now. More intensity, you will have more photon, and more photon will knock out more electrons, so you'll get more current. But then how you explain the residual or the reverse or the stopping potential, and why does it depend on frequency? So that requires a little more detailed discussion. So let us do that now. So what you understand is the atoms have a positive core. Remember that at this point Bohr's theory is still not there, and outside there is electron. Okay, so the electron sees a negative energy potential well Okay, so electron sees a negative energy potential well. So let me draw in y-axis. What I am drawing is energy. It can be potential energy or it can be any other energy, and this is potential equals to 0, and the electrons always see a negative energy, so the electrons can be up to this. So the electrons in metal can have maximum energy, say minus epsilon. So this distance is epsilon. Okay, this is the picture. Now, so if this is the picture, what happens if a photon of h nu falls in? Okay, let's ask the question, what happens if a photon of h nu falls in? So if I have an electron here just at the highest energy that the electron can have, the electron can be a little bit lower also, because all electron not need have the same energy. So this electron h nu, in the case 1, say h nu is less than epsilon. What will happen? If h nu is less than epsilon, this electron, on getting the full energy of the photon, will not be able to come out of the metal because it will still have some negative energy. The electron will remain trapped in the metal. However, if I give the electron energy which is greater than epsilon, so the photon which is coming up now, so nu 1, this is nu 2, definitely nu 2 greater than nu 1, and I have a photon which is hitting the electron which has energy which is greater than epsilon. So what happens? The electron comes out of the electron comes out of the metal. So when will I say that it has come out? When it has positive energy, right? It has positive energy. Why is that? Think of it. The total energy of the electron will have some kinetic energy and some potential energy, right? The kinetic energy is always greater than zero. The potential energy can be anything. So if the electron has some kinetic energy which is greater than zero, outside the metal it need to have some kinetic energy which is greater than zero. For that, its total energy has to be greater than zero. Otherwise, there is no way you can have a kinetic energy greater than zero. So that's why I say that it has to come out. It can just come out of the metal. It has positive kinetic energy. Positive energy is the kinetic energy. So the excess energy or the kinetic energy after it is ejected from the metal, how much will it be? Well, it had this h nu amount of energy. Let's call h nu. So nu is greater than epsilon. H nu is greater than epsilon, and epsilon amount of energy is used up in the metal for it to come out. So this is the excess energy, excess kinetic energy that it has. Now for this electron, now assume that this entire energy, with this entire energy, the electron is going from the from the cathode towards the anode. So now I have to give an opposite energy to this to stop the electron. So this h nu minus epsilon will also corresponds to the maximum kinetic energy of the photoelectron. And as you can see, the maximum kinetic energy now depend on the frequency, and it is proportional to the frequency. Okay, this quantity epsilon here, this will depend on the metal, which metal I am using, and this is, you can think of, this is the amount of work that the photon has to do to make the electron come out, if you can think of this way. So this is called the work function of the metal. Okay, sorry, I'm going a little bit over time, so we have just 2 minutes more required in this discussion. I will complete that and stop. So Einstein predicted the following. Okay, see, first of all, he explained all the previous phenomena. The first two were done by here itself, and then the fact that the maximum kinetic energy or the stopping potential depends on, so this is also equals to E times the stopping potential. It depends on nu is also explained here, and you see that this EV0 only depends on nu, it doesn't depend on how many photons. Because of that, it will not depend on the intensity of the light, as we have seen here, right? So all these were explained, And if you look at this curve, he said that now you can do this experiment where you use different frequency light and calculate the stopping potential. Okay, so what will you see? For one frequency, sorry, if I use different frequency for one metal, epsilon is fixed. So you can plot nu versus V0, that will get a curve like this. And this curve will have a slope which is given by h by E. So h is the Planck's constant. Now you see, Planck's constant came from a complete different, explaining complete different observation of photoelectric effect. Sorry, black body radiation. Einstein is predicting that you will see the same constant sitting over here for the slope of this line. If I extrapolate this in the backward direction, what will I get? Well, if you compare this with y equals mx plus c, you see c is the intercept. So this is essentially will give you minus epsilon. So if I use another metal, so this is metal 1, this is metal 2, it can have a different work function. So this is epsilon 1, I'm sorry, this is epsilon 1 and this is epsilon 2. So this is another metal. So different metal work function you can figure out like this, and if you actually do the experiment, you will see the slope to be h by E. Now this is a new prediction now, and it was first checked by Millikan in 1914. Checked that this actually is the case, and in 1923 and 1921 Einstein and Millikan were awarded Nobel Prize for this experiment and explanation of the photoelectric effect. So now you see, we have taken quite some extra time today, but we see that the radiation, which was initially thought of as continuous waves like thing of electromagnetic wave, required to be assumed as being the energy being carried and transmitted in packets, where each packet has an energy proportional to its frequency. And that is completely new physics that was coming up, and this is what was later termed as quantum physics, because we are talking about light quanta here, and we'll talk about quanta of other things in the course. Thank you.